Using chords. So we've talked about what it means to be a chord. Today we're going to be talking about how to actually use some of the theorems to go along with the chords. So the first theorem we're going to look at is talking about congruent corresponding chords. And this is pretty much common sense. What this says here is that if you have a chord like BC that is marked as being congruent to chord CD, then the arc that's made will be congruent to the arc that's made by that guy. And that should make sense that if the chords are congruent, then obviously the arcs are going to be congruent. So we come over here to the example. Here it says that if circle P is congruent to circle Q, so they're telling me these two circles are congruent, and they're telling me that FG, that's a chord, is congruent to chord JK, to find arc FG. Well, they tell me that arc JK is 80 degrees. Well, since I know that the chords are congruent, I know that the arcs have to also be congruent, and so this guy would also be 80 degrees. Pretty much common sense there. The next one we've kind of already talked about also, and that's the perpendicular chord bisector theorem. This says that if your diameter, if you're going through the diameter, and you are perpendicular, so we see that right angle right there, if you are perpendicular to a chord, then the diameter will bisect that chord so that this little piece of the chord will be congruent to that little piece of the chord. It will cut that chord in half so that my two halves will be congruent. And then if my two halves are congruent, if this segment is congruent to this segment, we're kind of going to piggyback off of this theorem and say that if this segment is congruent to this segment, then this arc is congruent to that arc. Okay? And then the last one here says that if you have a chord, so my chord here is perpendicular, all right, has a right angle right there, and is being bisected. So we have a perpendicular bisector thing going on like we had up here. Well, the only way for this to happen is if SQ was the diameter, just like we talked about on the previous one. The only way you're going to get this perpendicular bisector thing is if this is your diameter. I didn't know he was my diameter because I don't see him going through the center, okay, in the picture. But the only way that's going to happen there is if he is going through the center, all right? So we're going to apply that over here. And we see that JM is a diameter because he's going through the center. And I see that he is being perpendicular to HK, all right? So I'm going to apply theorem 10.7, which says if you go through the diameter and you're being perpendicular, then that's going to bisect this chord. Well, they tell me that this side is 7, so then I know this side has to be congruent, so this side is also 7. So first question says, how long is it all the way across from HK? Well, this half is 7, the other half is 7, so all the way across HK would be 14. That's a chord. HK is a chord. And now we're going to use this property here, well, kind of both of these properties, I guess you could say, that if the chords are congruent, the arcs are congruent. So since we've established that this half of the chord is congruent to this half of the chord, I know that this arc will be congruent to this arc. Another word for congruent is equal. And so 11x from that arc will equal 70 plus x of the other arc. And I'm just going to solve this here. I'm going to subtract x. So this is 11x minus technically 1x. Makes 10 x's. Divide by 10. And I get that x equals 7. But I'm not finished. That's not the answer to the problem. The question said, what is the measure of arc HK? So now I'm going to have to come up here, and everywhere I see an X, I'm going to have to substitute in the 7 that I just found. And I figure out 70 plus 7, that this arc is 77 degrees. If I plug in 7 here, 11 times 7, I see that that arc is also 77 degrees. That should make sense to you because we already knew that both of the halves of the chord were congruent, so the arcs should be congruent. So to answer the question, what is the measure of arc HK? Well, that piece was 77 degrees and the other piece was 77 degrees. So all the way across, arc HK is 154 degrees if I just add those together. All right, one more theorem. And this is the hardest one, I think. It's the equidistance chords theorem. What this one says is that chord AB will be congruent to chord CD if and only if they are equidistant from the center, meaning the distance between the chord to the center and this distance between the chord and the center have to be equidistant, which means congruent, which means the same. All those words are kind of interchangeable, okay? That distance between the center and that chord has to be the exact same. And so if we apply this here, I look at this and I'm like, okay, they tell me that QR equals ST and that both of them are 16. Well, if they are equal, the only way that that's happening is if they were equidistant. Okay, so if they're telling me that the two chords are congruent, this theorem up here says the only way for the chords to be congruent is if they are equidistant to the center. And so that's telling me that this little piece here, okay, showing me the distance to the center, must be equidistant to this little piece here, equidistant. So if they're equidistant, that means they are equal to each other. And so I can set up an equation that 2x equals 5x minus 9. Going to solve this for x, I'm going to subtract 5x. Gives me negative 3x. And then I'm going to divide by negative 3 and get positive 3. That's not our answer though. We have to plug that back in everywhere we see an x. And so I get that this little piece here is 6. Now, the question is asking me to find the radius of the circle, okay? So I'm looking here. I don't have any radiuses going on, but what I'm going to have to do is I'm going to have to draw in a right triangle. And so when I do this right here to draw my right triangle, it should make sense that this is my radius. So I'm going to kind of extract that right triangle and kind of draw him over here so I can understand the different parts of him a little better. So that was my radius. This little small side here was our 6 that we just found. And for the longer side, we're going to have to come back up here. And remember, they had told me that QR is 16. So this piece of my right triangle will be half of that. So it is 8. And so now I can use Pythagorean theorem to find the radius here. So we do 6 squared plus 8 squared equals r squared. That's 100 equals r squared. Take the square root of both sides, and we see that our radius is 10. Pause the video here and see if you can set up the next problem. hopefully you recognized now that we would be equidistant here because they've told me that the two chords are equal. And the only way for that to happen is if my distances are equal. So setting those equal to one another, I was able to solve and see that x equals 3. If I plug that in, then I will see 3 times 3, that is 9. Again, they want me to find the radius of the circle. And so the radius is from the center to the edge of the circle. So this would be my radius. I can label that R. I know the little small side here, I just figured out, was 9. Now I got to do a little bit of thinking for this side here. But they had told me that from J to K, JK is 24. And so I know that this will be half of that, and so that is 12. So if I kind of pull that triangle off so I can kind of see what's going on a little better. All right, so we have 12, we have 9, and the radius will be the hypotenuse there. So we do Pythagorean theorem. Take the square root of both sides, and you see that the radius is 15.